Today we're going to cover Step Paper 1 2001 Question 1 and Step Paper 1 1988 Question 3, which are essentially the same question. In order to get to grips with this question, we have to note that one of the vertices of the triangle can be coincident with one of the vertices of the square. So if you look at this diagram, here we have a square, edge 1 unit, and inside it I put the triangle. So that is 1 unit along there, that is x, that is y, 1 minus y, 1 minus x. Now we are required to prove that the length of at least one edge must be less than or equal to root 6 minus 2, root 2. So I proceed by contradiction. I assume that they are all greater than this length, so that x squared plus y squared is greater than root 6 minus root 2 squared, that 1 minus x squared plus 1 squared is greater than root 6 minus root 2 squared, and that 1 minus y squared plus 1 squared is greater than root 6 minus root 2 squared. Now, root 6 minus root 2 times root 6 minus root 2 is equal to 6 minus 2 root 6 root 2 plus 2, which is 8 minus 2 root 12, which is 8 minus 2 times root 4 times root 3, which is 8 minus 4 root 3. So, recomposing our sums, we have x squared plus y squared is greater than 8 minus 4 root 3. We have 1 minus x all squared plus 1 squared is greater than 8 minus 4 root 3. And we have 1 minus y squared plus 1 squared is greater than 8 is greater than 8 minus 4 root 3. And if I take 1 off both sides of each of the last two, I finally end up with this set here, which is x squared plus y squared is greater than 8 minus 4 root 3. But 1 minus x all squared is greater than 7 minus 4 root 3. And that 1 minus y all squared is greater than 7 minus 4 root 3. Now, two minus root 3 squared is 4 minus 4 root 3 plus 3, which is 7 minus 4 root 3. So, if I label my equations 1, 2, and 3, and if I take 3 and I take the square root of each side, the positive square root, I get, I get 1 minus y is greater than 2 minus root 3, which means that 1 plus root 3 minus 2 is greater than y, so y is smaller than root 3 minus 1. And because equation 2 is exactly similar to that, except that the subject is x, we can now conclude that x is less than root 3 minus 1. Now, according to equation 1, according to equation 1, x squared plus y squared is greater than 8 minus 4 root 3, which would mean that if we now look at the results I obtained here, we have root 3 minus 1 squared plus root 3 minus 1 squared. Our results so far imply that this should be greater than 8 minus 4 root 3. Now, root 3 minus 1 times root 3 minus 1 is 3 minus 2 root 3 plus 1. So the left-hand side would be 4 minus 2 root 3 plus 4 minus 2 root 3. So that implies that that is greater than 8 minus 4 root 3. But if we look at the left-hand side, we see the left-hand side is actually 8 minus 4 root 3. And that implies that this number is greater than itself. And that is a contradiction, and so I have now proved by contradiction that at least one of those lengths must be less than or equal to root 6 minus root